Hello students, A2 Chemistry, chapter is Chemical Energetics, lecture number 5. In this video, we are going to talk about the most important topic of the chemical energetics for A2, it is Born-Haber cycle. So this is the most important lecture we are going to start with. What is Born-Haber cycle? To start with, what you can remember simply Born-Haber cycle, it is an extension or application of Hess's law. So basically, we are going to study Hess's law in some more detail under the heading of Born-Haber cycle. Or if you want to remember what is Born-Haber cycle in more simple words, you can remember Born-Haber cycle as energy diagram for the Hess's law. So whatsoever we learn in the Hess's law, in the Born-Haber cycle, we apply that information, we sketch that information on an energy diagram. So energy diagram for the Hess's law, it is known as Born-Haber cycle. Before we proceed students, I invite all of you to subscribe my channel and uh, please also push the bell icon. Okay, let's start. uh, there are two typical questions that are asked in your A2 syllabus for the Born-Haber cycle. One question that is asked, it is to construct or to sketch and label Born-Haber cycle for the formation of ionic compound. This is one typical question that is asked about the Born-Haber cycle in your A2 exams. Second question that can be asked, to construct or to sketch and label Born-Haber cycle for the formation of ionic solution. And before we start sketching, before I explain how to construct Born-Haber cycle, let me give you again a quick revision about the Hess's law. As I told you in the previous lecture, what you must remember about the Hess's law, there are two important information that you must always have in your mind. What is Hess's law? One thing that you must remember, according to Hess's law, every chemical process can take place through two different paths, direct path and indirect path. What is the difference between direct path and indirect path? Direct path means that chemical process takes place, can be completed through one step only. Whenever a chemical process, it can be completed using one step only, it is known as direct path. And whenever a process it is completed using more than one step, it is known as indirect path. This is one most important information that we always remember from the Hess's law, that every chemical reaction, every chemical process, it can involve two different paths, direct path and indirect path. Second information that we remember, that we learn from the Hess's law, even that is more important, and that information is enthalpy change of the direct path, it is always equal to the enthalpy change of indirect path. So these are the two important information that we must have in our mind. Then we can construct Born-Haber cycle easily, and we can apply Hess's law on the Born-Haber cycle to derive a formula for solving numerical problems for the Born-Haber cycle. Okay students, we will proceed with the first example of this lecture, where I will explain how to construct Born-Haber cycle for a given ionic compound. So this lecture is particularly for sketching and labeling the Born-Haber cycle for the formation of an ionic compound. And we will start with the sketching for the construction of Born-Haber cycle for the formation of aluminum oxide. Okay, as I told you in the previous lectures, that aluminum oxide, which is an ionic compound, through the direct path, it involves one step. But whenever you want to prepare aluminum oxide using indirect path, there are three steps. What are the three steps? Step number one, atomization. Step number two, ionization. Step number three, formation of ionic lattice. And you must also remember, you must also know what is the enthalpy change involved for each of these three steps. Okay, let's start. How we start sketching Born-Haber cycle? First of all, we draw a line, an arrow directed upward. This arrow represents the level of energy. That energy is increasing in the upward direction. Close to the lower end, you will place a horizontal line. This horizontal line is used to place the position of the reactants from which the given compound is produced. For example, in this case, aluminum oxide, you can see that it is made up of aluminum and oxygen. So that is why aluminum and oxygen will be placed on this horizontal line. Next thing you can see from this line, an arrow, it is going downward. What is the reason? The reason is, always remember, standard enthalpy change of formation of an ionic compound is always exothermic. Standard enthalpy change of formation of an ionic compound is always exothermic. So that is why, since the process of formation is exothermic, the arrow, it is going down, the energy, it is decreasing, and we will place another horizontal line at the head of the arrow. This horizontal line is the position where we will place the compound, the product formed, like Al2O3 in this case. Okay, let's start. If this is as I have told you, this is exothermic reaction, so that is why we have gone down. If ever you are given some endothermic reaction, the arrow from the same position, it will move upward for the endothermic reaction. Okay, I will give you example in some later lecture. Okay, right now, you will place products at the lower position. The product is aluminum oxide, Al2O3 solid, and this aluminum oxide, it is produced by combining aluminum and oxygen. You can balance aluminum and oxygen by you can balance aluminum and oxygen. For 1 mole of aluminum oxide, for 1 mole of aluminum oxide, we must have 2 mole of aluminum and 1.5 mole of oxygen. 1.5 can also be written as 3 by 2. Now this is a balanced chemical equation for the formation of aluminum oxide, and it represents direct path. Why it represents direct path? Because it involves one step. Now to make it thermochemical equation, we will label it with the enthalpy change. And what is the name of this enthalpy change that is involved during this step? This is known as standard enthalpy change of formation of aluminum oxide. So students, you can see that we have completed the direct path for the formation of aluminum oxide using these using this equation. Now next we are going to write down equations for the indirect path for the formation of aluminum oxide. And as I have told you, for the indirect path, there are always three steps during the formation of ionic compound. Step number 1, atomization. Step number 2, ionization. Step number 3, formation of ionic lattice. So first of all, we will atomize. You can atomize these elements stepwise. In one step, you must atomize one element only. There is no problem. You can atomize these elements in any sequence. But I am atomizing, first of all, I am atomizing aluminium. Aluminium, it is a metal. What does atomization of aluminum mean? It means aluminum Al symbol and the state symbol must be gas. This is atomization of aluminum. And there are 2 mole, we will multiply it by 2 mole. At this stage, we are atomizing aluminum only. So when we are atomizing aluminum only, the oxygen, it will come up unchanged. So what you will write down? You will write down oxygen without any change. So it is clear from this equation, you can see there is a change only in the physical state of aluminum. So that is why on the reaction arrow, we will label the enthalpy change for aluminum only. So this enthalpy change is known as standard enthalpy change of atomization of aluminum times 2. Why 2? Because there are 2 moles of aluminum. Next come after aluminum, still we need atomization of oxygen. So we will move up again. Why we will move up again? Because atomization is always endothermic. Why atomization is endothermic? Because atomization involves bond breaking, and whenever there is bond breaking, energy is absorbed. So again we will move up, and at this stage now we will atomize oxygen. So aluminum, it will remain unchanged. Without any change, we will write down aluminum, and now we will atomize oxygen. Atomization means symbol of oxygen, state symbol gas, and we will get 3 mole of oxygen atom. So this step, you can see at the end of this step there is a change in oxygen molecule. Oxygen molecule has been broken into oxygen atom, so that is why you can label this step as standard enthalpy change of atomization of oxygen times 3, because there are 3 mole of oxygen atom. Now as you can see students, at the end of this step, atomization has been completed. Since there are two elements involved for the formation of aluminum oxide, so two times we have to do atomization. One atomization for aluminum and the second atomization for oxygen. Next come ionization. Again, you can do ionization for any element, depending on which compound is given, but conventionally metal is atomized earlier. Why? Because metals, they lose electron, and when metals, they lose electron, the lost electron, it is gained by oxygen. So that is why always whenever you will carry out ionization, remember metals must be ionized first of all. We are having aluminium metal. One aluminium atom, it can lose 3 electron. One aluminium can lose 3 electron. So what will happen? Aluminium will lose 3 electron. Aluminium will get a charge of Al3 plus. When aluminium will lose 3 electron, 2 mole of aluminium, they will lose total 6 electron. And what this enthalpy change is known as? Whenever electrons are lost, enthalpy change is known as ionization energy, and we are removing 3 electron. So this will be first plus second plus third ionization energy of aluminium. But we are having 2 mole of aluminium, so there will be 6 mole of electron. And oxygen at this stage, again it will remain unchanged, because we want to show ionization of aluminum only at this stage. And so what label particularly you are supposed to write down on this green arrow? This is ionization energy. This will be first plus second plus third ionization energy of aluminum multiplied by 2, because there are 2 mole of aluminum. Okay, now comes the ionization of oxygen, and what you can see there are 6 mole of electrons available, and we are having 3 mole of oxygen atom. Oxygen belongs to group number 6, and one oxygen can gain 2 electrons. When one oxygen will gain 2 electron, oxygen will become oxide ion having a charge of 2 negative. One oxygen will gain 2 electron, and 3 oxygen will gain 6 electron. So the number of electrons lost and gained, they will become equal. Second thing you must remember, whenever an element gains more than one electron, it involves which enthalpy change? First and second electron affinity. And we have studied in the previous lectures that sum of first and second electron affinity is always endothermic. So that is why we will keep on moving upward. And at the end of this arrow we will place line. At this position we will place aluminum unchanged. Electrons will disappear, because electrons will be gained by oxygen. Oxygen has become oxide ion multiplied by 3. So you can see all the electrons have been disappeared because they have been gained by oxygen. What the enthalpy change of this step will be known as? This is the enthalpy change This enthalpy change is known as electron affinity, and it is first plus second electron affinity of oxygen multiplied by 3. Now the last step, atomization has been completed, ionization has been completed. The last step of the indirect path for the formation of ionic compound, it is formation of ionic lattice. So ions will combine together, bond formation will take place. That is why energy will decrease. The arrow will go downward since this is exothermic. And what this enthalpy change is known as? This enthalpy change is known as lattice enthalpy. So students, you can see we have constructed Born-Haber cycle, and most of this information we have used from thermochemical equations of the Hess's law. So if you have watched the earlier lectures of this chapter, then sketching of Born-Haber cycle would not be a problem for you people. If someone is having some difficulty in understanding some of the enthalpy changes, he or she must watch the lectures that I have taken earlier for this chapter. Okay. Now students, we can also apply Hess's law to this Born-Haber cycle to derive a formula if ever we have been given some numerical problem. So for that, what I told you, you must identify what is the initial stage, what is the final stage. Initial stage, let's identify. Have you marked what is the initial stage? The initial stage is elements aluminum and oxygen. Why? Because two arrows are taking a start, and both the arrows they are having their tails at this position. So that is why this is the initial stage. And what is the final stage? Where both the arrows they are having their heads, that is aluminum oxide. This is the final stage. And what I told you, I kept on telling you again and again in the previous lecture, that for the formation of ionic compound, what is the resultant vector only? The resultant vector is always standard enthalpy change of formation. Always this will be the direct path for the formation of every ionic compound. Standard enthalpy change of formation is the resultant vector, and it is equal to what? Mathematically it is equal to atomization of aluminum multiplied by 2 plus atomization of oxygen multiplied by 3 plus first plus second plus third ionization energy of aluminum multiplied by 2 plus first plus second electron affinity of oxygen multiplied by 3 plus lattice enthalpy. So you can see we have constructed the Born-Haber cycle, we have also applied the Hess's law, and we have derived the formula for doing calculations. Okay students, let's practice some examples. I will give you some compound, you will construct the Born-Haber cycle for that compound, and you can also apply the Hess's law. That is not a problem, but basic thing is you must focus on to construct Born-Haber cycle properly without making any mistake. Remember, each and everything must be mentioned clearly, because if you miss out even a single information, you will be penalized for 1 mark. So you cannot miss out any physical state, you cannot miss out any labeling. So be careful. I'm giving you some examples, you can answer, you can pause the video, you can sketch it, and you can see the answer just to check how how many mistakes you have done. Okay, first example, sketch and label Born-Haber cycle for the formation of calcium fluoride. You can pause the video and you can sketch Born-Haber cycle for this. Okay students, if you have sketched, just check it out whether you have constructed Born-Haber cycle correctly or not. Energy level, direct path, enthalpy change of formation, atomization, atomization of fluorine, ionization, ionization of calcium, first and second ionization energy, Then ionization of fluorine, but here there is a change. Fluorine gains one electron. When fluorine gains one electron, which energy change is involved? It is first electron affinity. First electron affinity means that arrow will go downward. So that is why this arrow has gone downward. And this is first electron affinity multiplied by 2. And then there is the lattice enthalpy. Student, you can see there is one difference, that in this case fluorine has gained one electron only. That is why the arrow has come down, because this first electron affinity, it is always exothermic. All other steps, they are identical. There is nothing new. I hope you would have done it correctly. If you have made some mistake, you can correct them. Try to solve the next example and try to make the improvements. Sketch and label Born-Haber cycle for the formation of sodium sulfide. Okay, students, if you have sketched for sodium sulfide the Born-Haber cycle, it should be direct path, atomization of sodium, atomization of sulfur, ionization energy of sodium, electron affinity of sulfur, and the lattice enthalpy. In this example, what can happen? Some of you might have written S8. It is acceptable if you have written S8, but if you have written S8 when you have made the reaction of sulfur with sodium, you must balance it like 1 by 8 S8. So it makes no difference whether you have written simple sulfur S or you have written 1 by 8 S8. So in both ways it is acceptable. Okay, check it out. I hope you would have done correctly. One last example that you can practice, it is the sketch and label Born-Haber cycle for magnesium oxide. Okay, if you have practiced this time, check it. This is the direct path, indirect atomization of magnesium, atomization of oxygen, first and second ionization energy of magnesium, first and second electron affinity of oxygen, and lattice enthalpy. Now students, one more thing, in different books you might have seen what can happen. Look at the ionization of magnesium. Sometime what we do in case of magnesium, you can see there how many electrons have been removed by one magnesium, 2 electron. So how many ionization energy values are involved? 2. So what you can see in some books, that each ionization, it is performed stepwise. What does this mean? That they show removal of first electron, first ionization energy, formation of Mg1 plus, and after that from Mg1 plus to the formation of Mg2 plus, second ionization energy. So it means you can break up the ionization energy step into two or more sub steps depending on the number of ionization energy values. That is not a problem, but for simplification I always prefer that my students, they must combine all the ionization energies and they must combine all the electron affinities. It is acceptable, there is no problem. Okay students, I am giving you some examples as home assignment. You can practice these. Some examples where you will have to construct the Born-Haber cycle for NaCl, AlN, Na3P, AlF3, and Mg3N2. Okay, these are the some examples that you can practice just to make your understanding better. Thank you for watching. Bye for now.